Hi, as I was already mentioned, I'm Kostas, and I will be talking about the research I have been doing for the past 2.5 years or so that I have been at LNL as a member of the Nuclear Data and Theory group. So if I manage to change slides, um, the goal of the Nuclear Data and Theory group is to take experimental data, combine them with whatever theories available for specific processes, and then provide an accurate evaluation that can then, for those nuclear data, that can then go on and be used by applications. And applications here mean anything from, for example, a neutron transport code that will do a simulation of a reactor or something. Um, Naturally, there is not a single theory that can be used for all nuclei and for all properties across the nuclear chart. So there are different ones for different regions. So fission theories usually mean field theories, but I will be focusing on ab initio nuclear reactions, which is what I mostly work on. So the goal of ab initio nuclear reaction theory is to be able to predict reaction observables for light ion reactions. Hopefully, we would like to do not only light ion reactions, but it's generally computationally very expensive. So we focus on light ion reactions. And for example, here, DT fusion is a reaction that produces energy in the sun and in possible fusion reactors. So deuterium comes in, fuses with a tritium, produces helium-4 plus a neutron, releases energy. These are the type of reactions that we would like to be able to simulate and have a predictive theory for. As an example, we can look at the helium burning process from a more basic science side of things. So in the helium burning process, two helium-4 nuclei fuse together for a brief 10 to the minus 16 seconds, forming an unstable 8 beryllium state. Then they can capture another helium-4 particle, form carbon-12, which can then capture another helium-4 particle and form oxygen-16. And it's the precise ratio of reaction rates at each of these steps that will determine what is the final ratio of carbon to oxygen in the universe. So it is important to have a good modeling of these reactions, because it's not as simple as going out and measuring them if we want to find elemental abundances. And it's not simple to measure them simply because the energies that are relevant in nuclear astrophysics are essentially very low. So your reaction rate is hindered by the Coulomb repulsion of the two reacting nuclei. I'm having here as an example helium-4 fusion with carbon-12. So you see at higher energies, there's a lot of data points, there are small error bars, the reaction is relatively well understood. As you move to lower and lower energies, experiments become sparser, error bars become larger. So it is important to be able to extrapolate down to low energies. And this is where the predictive theory comes in. If you have a theory that can absolutely describe the experimental data up here, you can be confident that when you use it to extrapolate to low energies, it's something that you can actually trust. And in a more grand scheme of things kind of way, it is something, the eventual product that you would like to use is something that fuses experimental data with the predictive theory so that you can get a reliable extrapolation with a quantified uncertainty. Because a theory prediction on its own, just a simple line going somewhere, is of limited use at the end of the day. If you don't have a handle of how well you actually know that extrapolation, then it's not very helpful. So that's not all that we're interested in with ab initio theory. So one of the cool things you can do with ab initio theory is, at the end of the day, your fundamental degree of freedom is still the nucleon in ab initio theory. So what you can do is study the emergence of collective phenomena in nuclei and how these phenomena will emerge from the nucleonic degrees of freedom. And one of my favorites is nuclear clustering. It refers to the formation of substructures within an atomic nucleus. I'm showing as an example here beryllium-8 clusters into 2 alphas, 6 lithium, alpha plus D, and so on and so forth. You see that in most of these cases, the alpha particle is the fundamental building block. That is because, sorry, the alpha particle is just so well bound, right? So it has, if a system is to cluster, there's a high probability it will cluster into alphas plus something. Furthermore, you have cases like beryllium-9 or beryllium-10, where the alpha particles act in the same way as atoms do in covalent bonds, with the neutron being shared the same way as a valence electron would be shared between the two. These give rise to molecular, or what is believed to be molecular type structures, and then rotational bands build on top of them. So it's these types of states that we would like to be able to study. So how do you put in a bunch of nucleons, why would they form such a covalent bond? Um, Now you would expect to find these states traditionally close to thresholds. So this is the Aikida diagram, which essentially shows you precisely that. You have, let's say, 24 magnesium, you reach the alpha threshold, you expect to find states that are of the type 20 neon plus an alpha. You reach the next threshold, you expect to find 12 carbon plus 12 carbon and so on. But that's not the full story. There are other states higher up in the spectrum which are particularly broad, so they saturate all the alpha width for that decaying state. So we know they are clustered, but the question is, how do they survive? So as an example, again, in 12 carbon, you have a state that is 5 MeV above threshold approximately, but then it has a large alpha width. So it's still clustered somehow, but we really want to understand how does it survive the many-body complexity. Like, it's so further up in the threshold, it has no reason to be there, or probably it has a reason to be there, but we would like to understand why. And it's these types of structures that will affect your eventual cross-section for, say, alpha capture. So we need to be able to describe them well. Oh, actually, yeah, this sort of concludes the introduction, and now I can move on to modeling. So if there are any questions on the introduction, please ask me now. Okay, so how do we model this? How do we do the ab initio modeling of nuclear reactions? First, we need to be able to describe the internal structure of the reacting nuclei. We do that using the no-core shell model, which is essentially just make a harmonic trap, throw on all your nucleons inside. This will make the lowest Pauli allowed state, and then progressively allow more and more excitations out of that closed core with the least amount of energy. As you allow more and more excitations, the problem is that this becomes much more computationally difficult. So realistically, while we would like to have an infinite amount of excitations, we truncate this at some point and we say, fine, this is what the Nmax truncation that we're going to make. This is a very good approximation for most bound states, as long as they are well bound at least. So for example, if we have an alpha particle as the target nucleus, this would be a very good approximation of the ground state wave function of the alpha particle. However, we're doing reactions. So we not only need to be able to describe the internal dynamics of the reacting nuclei, but we also need to be able to describe the asymptotic states that we find them in. So way before the reaction, we have the two nuclei very far apart, they react, we find them again very far apart in the far future. So we need to have somehow this A-body configuration of two nuclei very far apart. And this is done, again, with the full A-body wave function. We construct these types of states. You can do this either placing the nuclei at varying distances from one another or in some definite relative motion to one another, which is sort of equivalent. So at the end of the day, the wave function of the full A-body system is described as a sum, where part of it contains these asymptotic states, this resonating group method type states with the two fragments definitely separated from one another. However, we also augment the wave function with no-core shell model type states for the A-body system now, not just for the internals of these two guys. And the reason is that as the two nuclei come close together, they will swell, they will exchange particles, they will deform. These are not easily describable within the resonating group method. They can be described in the resonating group method by including excitations of the two nuclei. but this increases computational complexity significantly. So that's not something we would like to do. While on the other hand, this type of description is very good at taking care of short-range correlations. So including those in the wave function is a lifesaver, actually. So bottom line, and I think this is the last equation. So the whole generalized problem looks like this. We have the RGM sector, which contains matrix elements of the Hamiltonian and the norm operators between these RGM type states. And then we have components that link these RGM type states to those compound Noether-Shell model type states that are there just to handle the deformation, etc. So this is the problem we have to solve. The unknowns are the coefficients in the expansion, the discrete coefficients C, and the continuum amplitudes U that are here and here. And we need to solve for them. And we do that using the microscopic R matrix. And the microscopic R matrix, basically, you take the distance between your colliding nuclei. You say, okay, at some finite point, these two don't feel nuclear interaction anymore. So we're going to solve for the inside and then match it to the solutions that we know on the outside at that matching radius that we have determined before. Typically for our calculations, just for your information, I guess, this is around 18 to 20 Fermi. So it's not, it's far enough apart that we believe there is no nuclear interaction anymore. There is a dual to the microscopic R matrix. You can also do this in function space. So if you expand the relative motion on a basis of functions, you can say, okay, I will break the expansion at a specific point and then match it to the analytic solution again on that Bayes function expansion space. So we sort of use both ways. It turns out the function expansion is helpful for us to actually compute the matrix elements that I showed before. So, or parts of the matrix element, but then we connect and go back into the normal R basis that we use to solve for the reaction observables. Does it actually work? The answer is, in general, yes. So I'm showing here proton scattering off of an alpha particle and deuteron scattering off of an alpha particle elastically. So in both cases, there is decent agreement with the data. However, there are questions. And one of the questions is, what about uncertainties, right? We have disagreements, for example, here. We overshoot the data here. The dip here is not exactly where the data are. So we would like to understand, is this a problem with the interactions that we use for how the nucleons interact with each other? Is this a modeling problem, or is this an experiment problem? Well, probably not an experiment problem. And also notice that this goes up to deuteron, and we would like to be able to do heavier projectiles as well. So we honestly would like to be able to do alpha particles because, as I said before, it's the main ingredient in nuclear clustering. So when you want to describe a clustered state, you better be able to handle an alpha particle projectile. So these are the main two foci of this talk, at least. I had to this point been pretty silent about how the nucleons interact with each other. In general, we use interactions derived from chiral effective field theory. The reason we do it is because chiral effective field theory is basically a bag of goodies. One, it provides us a direct link to quantum chromodynamics, which is the underlying theory. Hopefully with live simulations in the future, it will be an even better link. Second, the interaction is organized as a systematic expansion, which means that it's written into order of importance by order of importance type of way. And this means that if we actually truncate at a specific level, we have a handle of how much is the error that we're accumulating because of this truncation. So what are the physics we missed? There is a systematic way to handle this because it is a systematic expansion. Second, the three nucleon force that we already know is necessary to describe the nuclear, to describe nuclear properties arises organically. So at third order, you have three nucleon force diagrams. So that's also good from a personal perspective, right? You you're at least doing something right. Finally, there's only a handful of coefficients that define the whole interaction that will eventually be fit to some nucleon-nucleon experimental scattering phase shifts or 3 nucleon properties or even other things that I'm not going to discuss here. So because there are just so few parameters, it means that we can actually go ahead and do a more robust uncertainty quantification on how these parameters actually, the uncertainty in these parameters actually translates to uncertainties in our observables. I say few parameters because I come from a shell model background, so fitting 100 of parameters is not unheard of in the shell model space, but here it's less than that, around, let's say 40. So obviously, solving a system of A nucleons with nucleon plus 3 nucleon forces is computationally very expensive. It's expensive to just do structures. Reactions is even worse. So we have been lucky in the past few years because GPU accelerators have been made an integral part of high-performance computing architectures. So what I'm showing here is a node from the Summit supercomputer, or the anatomy of a node. Summit was one of the top supercomputers for the past couple of years at least. I forgot when it dropped from #1 because time has become a blur. You will notice the main thing here is that for each CPU in the node, there are actually 3 GPUs. These doesn't look like a normal graphics processing unit that you plug in your computer. It's actually soldered on because there are different types. But the main point to take away here is that as the architectures evolve, graphics processing units moved from accelerators, where you would simply offload a little bit of your calculation, to being the point where you have most of the compute power within a high-performance computing node. So it becomes important to be able to effectively take advantage of graphics processing units in your calculations. And we have done exactly that. So what I'm saying on the left is speedup that we obtained from GPU accelerating the no-core shell model part of the calculation, so solving for the bound states of the nuclei. This is an okay speedup, about 5 times what we used to actually have. However, the real speedup came when computing the matrix element of the RGM type of states. This is not a simple porting, so it's not like OpenMP where you go add a few pragmas into your code and everything is suddenly faster. This required significantly reworking of the internals of the code, replacing algorithms, and in fact, the formalism had to change on how we compute reactions. So we moved on to a second quantization framework for computing the nuclear reactions and couplings. But I'm not going to go into too much detail about that. All I like to point out is that not only we obtain a good speed up, what is here lower fidelity and higher fidelity are basically truncations in the 3 nucleon force. And what we actually have is sort of a similar runtime, regardless of how many matrix elements of the 3 nucleon force we use. So this is good for us because we really wanted to push forward on that front. So naturally,
sorry, Kostas,
yes?
do you mind if I briefly interrupt?
Yeah, sure.
So these runtimes that you have here, are they for the same number of CPUs and GPUs? I mean, how do you renormalize the number of cores that you're using in the computation?
I used a node.
So per node. So this is per node.
No, this is per 32 nodes, or are you looking here? So in both cases, there's the same number of nodes, either on the CPU or the GPU. So a node here has 40 cores and 4 GPUs. I don't remember exactly the number of nodes used in these calculations here, but here they're written. Is that?
Thanks.
Cool.
Thanks.
I know in principle that's not necessarily a good metric because usually GPU nodes tend to be more expensive. But I think even if you were to correct for that, it would still be an overall speed up. So for example, if you were to have only a pure CPU machine, it would have roughly twice the number of nodes just because of cost. But then you still get, for example, here you get a ×7 speed up, which is not, it's pretty decent. So yeah, that's basically, well, the other problem is that it, as you move on in HPC architectures, becomes more and more difficult to find high core count machines since they are all moving over to GPUs. Wow, I realize time is passing. Okay, sorry. So the first thing we would like to do, having implemented improvements in the code, is actually run the code multiple times, which means uncertainty quantification. Now, that was sort of a joke. That's not why we do this, but okay. So yes, we would like to be able to understand where the uncertainty is coming from in our calculations. And we believe that for internal reasons, let's say, the coefficients that come in the three nucleon force diagrams, or the one pion exchange diagram and the contact diagram, CD and CE, are a source of uncertainty, while the nucleon low energy constants are fit to two nucleon scattering where there is abundant data. These are essentially fit on the triton half-life and the triton binding energy for us. So what I'm showing here on the left is the ratio of our calculation versus the experimental half-life for the triton with various values of CD. And you can focus on the red line, for example. So if you don't care about uncertainties, you would say, okay, which value of CD does this intersect 1? And that's going to be my value of CD. If you wanted to do some minimal uncertainty quantification, you would say, okay, there is some experimental uncertainty. So I will take, which is this actually blue band here. So I will take wherever the line intersects with the blue band, and that will be my uncertainty for CD. Using the triton binding energy, I can also get the corresponding values for C. However, realistically, this uncertainty for the experiment is too narrow. I'm not saying that the experiment doesn't have that uncertainty. I'm saying that it constrains CD way too well for what the theory is. There are inherent problems, not problems, there are inherent uncertainties with every theory. So physics you've left out, for example, and we have, because we know from the chiral EFT expansion that there is some physics we left out. So essentially, it could be that we are overfitting in our choice of these parameters. So we augment our chi-square with a theory term. In the shell model, this was pretty standard when you fit shell model interactions, because these would include, you expect your model to be good up to 200 kV. Here, this is a measure of how well we believe chiral EFT is able to describe this process. So this red band is actually the theoretical error we expect at N3LO, and the green band is the theoretical error we're expecting at N4LO. So now we get a much larger error band for CD and correspondingly for CE. If we want to explore this pretty much huge space of parameters, we would need to do multiple calculations, which is not realistically feasible. If a calculation takes a day, you cannot do tens of thousands of calculations that we would need for a Markov chain Monte Carlo sampling. So what we do is we build emulators for the computational model. We do this using Gaussian processes. I'm not going to spend a lot of time discussing emulators, obviously. The whole point is you have an interpolator. So you have you have inputs X, outputs Y. What essentially the Gaussian process model will make for you is given three experiments, let's call them, or calculations for us. It will construct a model that returns a mean value and a standard deviation around that mean value based on those 3 points. So it has no knowledge that the exact model here is a straight line, but as you add more and more calculations, you can actually obtain a very good interpolant. It's definitely not a good extrapolant, I can tell you that. Okay, originally, this is our prior. Basically, this entire plane of all CD and CE values that we deemed acceptable. And we want to see what uncertainty this corresponds to for reaction observables. So one of the more straightforward reaction observables that we calculate is an alpha scattering, the total cross-section. So what is shown here is as we progressively add more and more constraints, in our on CD and CE, how does the uncertainty of the total cross-section change? So originally we added the helium-4 binding energy. This gets rid of all this region, but there's still quite a bit of uncertainty in the total cross-section. We add the charge radius. It doesn't really do much. It clears up here, but it shifts most samples here. So this is the posterior distribution for the CD and CE samples. This shrinks a little bit the uncertainty down here, but doesn't do much here. And finally, in order to somehow constrain this thing, we add the resonance positions and widths of the 5 helium system. So this is what really constrains the N alpha cross section. It brings us really close to NDF, which is a little bit to be expected. And it brings us to close agreement with experiment. What is sort of good news is that we're very close to our original estimate for CD and CE. However, this is pretty broad of a distribution. So in the future, we would like to have this better constraint. One downside is that you might have noticed that this is a lot of points. So we have to do a calculation at each of these points. Oh, a hand. Hello, you can unmute, I guess. I don't know how this works.
I think I can unmute. Hi.
Cool. Hi.
So I wanted to ask about the box, right? So when I see a box on a plot like this, I don't know how to interpret that in terms of a probability distribution or a confidence.
This one, right?
Yes, exactly, right.
So like 95%.
So, but then why is it a box?
Because we made it so that it's a box. So
it's not really a box.
No, it's not. Well, the posterior is what it is. But if you want to give two numbers, people want two numbers, right? So you want SED plus minus that.
So that is the.
If someone doesn't want to use the full posterior.
That's the two one-dimensional 95% intervals. It's not the two-dimensional posterior.
No.
Okay, because I mean it's clear, as you said, it's clear from the shape that the that the
If
alpha particle constraints give you a strong correlation between CD and CE, right? Yeah.
Yep. If someone wants to use the full posterior, by the way, I think it's a supplemental material in the paper. Yeah. But yeah, it becomes a little bit unwieldy, right?
Yep. So then the other question I had is, so those theory errors that you talked about as being important,
these guys
back here. So have you also accounted for those when, using the N alpha data as a constraint on?
Oh yeah. So for example, I don't know if how familiar you are with the system. I don't want to assume, but there is a narrow resonance at 3/2 minus and a much broader resonance of 1/2 minus. So for the narrow resonance, we're much more confident that we can correctly extract the width, for example, and the position. For the broader resonance, the algorithm that we have for extracting might not be as good. So that is also taken into account.
But you have like order by order resonance positions and widths that help you to quantify the truncation error from chiral EFT for those quantities?
We did not include that. So this is only within that chiral EFT order. We did do a chiral EFT uncertainty estimate, but it was separate from this estimate.
Okay, thanks.
You're welcome. And I also see Philomena has her hand up.
I also have a question, if you don't mind. We're interrupting you a lot. So I had a question about this choice of this cluster of training points in the middle and then training points outside. I read your paper and I know you did this, but can you tell me more about why that was a wise choice? Why did you need those so many, such a high density of training points around those values?
Okay, I wouldn't call it a wise choice, but so the reason there are more points here is because this is closer to our original value. So we wanted.
But aren't you worried you're biasing the results towards your original value then?
Oh no, right? Because this is an emulator. So at the end of the day, we're sampling across the entire space. So all we have is a much better emulator in this region than anywhere else. So I don't think we're biasing.
Okay, because you believe that's the physical, that's where.
Yes.
Okay.
Ideally, I would have a similar sampling rate everywhere else. And actually, it was a bit of an iterative process of once you have constructed these points where these points were not, if I remember correctly now, were not all constructed at once. So we find, where are we missing? Where do we have a higher variance for the emulator? And then sample at that point. Okay. Yeah, so as I was saying, these are about 80 points, if I remember correctly. So realistically, N alpha is relatively cheap to calculate. The problem is that if you have a bigger reaction with heavier nuclei, it is not feasible to compute in all those 80 points. So what we're doing now, and I should really acknowledge Kevin in this because he's the one pushing this forward, is we're trying to look into mixed fidelity modeling, and the first results are kind of exciting, so encouraging, I should say. Out of all the points that we have, we say, okay, we will do a full calculation only for, let's say, the blue points here, and then for the rest, we will do a low fidelity modeling. Low fidelity modeling for us means doing the calculation at the lower Nmax. We know that at the lower Nmax, we can sort of extrapolate or say what the uncertainty is by looking at the higher fidelity calculations. We have the higher fidelity and the lower fidelity, and we know this should be relatively independent, how one goes from one to the other, regardless of value of input parameters. So we can build a model for it. And then this actually translates into a smaller root mean squared deviation. And in fact, it's quite happy that we see a reduction in the average root mean squared deviation with just a handful of high fidelity samples. So at 5 high fidelity samples, we've already dropped quite significantly in the average RMSE. So this is a promising way, at least for us, to move forward, because at the end of the day, if we have a heavier reaction, like, for example, the alpha-alpha, even on the alpha-alpha, we can probably do like 60 samples, but still, it's sort of a waste of computational resources at the end of the day, if you can do the same thing with a lower fidelity. So this is where we are with the uncertainty, and now I would like to move on. Okay, times, okay. So move on to the alpha scattering stuff. So, okay, I talked about helium burning in the beginning a little bit. First question is obvious: can ab initio theory be used to describe helium burning? The answer is yes. Pioneering work by Serdar El-Hatissari, whose name I hope I didn't butcher, and collaborators showed that you can actually do ab initio theory to do, for example, alpha-alpha scattering. So this is at least one path forward to actually computing the reactions in the helium burning chain. And also alpha-alpha scattering is sort of the go-to problem if you want to do alpha-induced reactions. It's the easiest reaction you can do. So where are we now on that? So we have implemented the new techniques based on second quantization that I mentioned about for the RGM part of the wave function. So we can now compute RGM matrix elements, which, believe it or not, are the main computational time sink for computing reactions. We can compute these relatively fast on GPUs. We haven't extended it yet to the no-core shell model with continuum, the full no-core shell model with continuum. So we just need to find time to sit down and write the code that computes those couplings. But nevertheless, we can still make some good research based on just the RGM, where we are now with alpha-alpha. So what is shown here is phase shifts and differential cross sections for alpha-alpha scattering with 3 different nuclear models. Overall, I would say the agreement with experiment is decent. Like at this level, I would say anything is good as long as we obtain sort of the spectra. The NN interaction only is already at a very good level, showing you that the 3 nucleon force on its own wouldn't expect to be a significant player in how the 2 alpha particles interact with each other. However, what we found out is by using 2 different models for the 3 nucleon interaction, namely one that is regulated with a local regulator and one with a local and a non-local regulator, the behavior changes dramatically. So with the local, everything seems to become much more bound. So the 2+ resonance, for example, shifts to lower energies, whereas if you use the non-local regulator, you actually shift more to the correct energy of the resonance. And this is something that one would say, of course, we should have expected this, but we believe it's actually linked to the fact that the 3 and local interaction actually overbinds things as you move on to heavier systems. So this was one of the reasons actually the non-local exists. So overall, the agreement with experiment is nice. I personally think that alpha-alpha scattering, actually an emulator of alpha-alpha scattering, might be useful in fitting next generation interactions because of this feature, because it can show you, it can act as a decider over how interactions will fare when it comes to heavier systems. But that's not all. Thanks again to the new implementations. We can now do reactions with P-shell projectiles. So this was a very qualitative example that we did of 12 beryllium. So in 12 beryllium, you have various modes the system can clusterize. And here progressively, we are adding more and more of these clusterizations of 12 beryllium. So we have 6 helium plus 6 helium originally, then 4 helium plus 8 helium. Then we combine the 2, and it's simple 2-level state, 2-level mixing. So the 0 pluses, stretch apart. The 6 pluses here do the same. Others remain unchanged. But the real interesting thing comes in when we add the 11 beryllium plus neutron partition to the system. So we see a couple of things that are interesting. First of all, these 6+ states remain as they are. They remain essentially unchanged. This is interesting in the sense that these are states that are way above the whatever decay threshold they are, yet, for example, this one remains surprisingly narrow. This is not something that one would necessarily expect. I mean, there's still some high angular momentum barrier, but it's nice to see a member of a rotational band, because we know it's a member of a rotational band, to survive this way up in the continuum. So that's one piece of interesting physics. The other thing is this 2+ right here, which becomes surprisingly broad. And this is also, I personally liked it, because it's essentially an interaction through the continuum. You include the 11 beryllium plus neutron channels, which creates a new way for the cluster configurations of the 4 helium plus 8 helium and the 6 helium plus 6 helium to interact with one another. And this causes a rearrangement in the wave function, which in turn corresponds to that increased width. Again, this is still pretty far from threshold, but it's still clearly clusterized. And we see it in the 6 helium alpha 8 helium transfer reaction. Okay, so to sum up, where are we? I started with talking about the alpha helium chain. We've completed this first step, or pretty close to completing it if you count the no-core shell model with continuum that we haven't done yet. We are currently working on the 8 beryllium plus 4 helium. Do not have a pretty plot to show, or all I have is anecdotal statements that we actually do see a Hoyle state close to where the Hoyle state is expected by just including the ground state of 8 beryllium and helium-4 scattering. We're also working on the 12 carbon plus 4 helium, but that's more of a computational challenge than anything. We expect to be able to tackle this with exascale computing. Essentially, it's a much bigger problem, but it's much more sparse, which sort of helps. So overall, that's basically it for astrophysics. Yeah. So I have 4 more minutes. I think I can make it. Okay, so I talked a lot about nuclear data in the beginning, but then I focused on astrophysics. And astrophysics is only one small part of where nuclear data is applied. So in fact, you have applications in medical physics, border security, stockpile stewardship, reactor design, and fusion reactor design. So these are all places where nuclear data is used. And it's a question of how can ab initio theory, reaction theory at least, help in all of these points? How can we help the USNDP? And if this was a live talk, I would say something like what's common between these two pictures, but this is not a live talk, so I cannot do that. So what's on the left is actually a standard, so it's a kilogram. What's on the right is also a standard. It's the 6 lithium N-T reaction. And a standard is essentially defined by, for example, in the kilogram, you can take another object, weigh it against the kilogram, and figure out how much it weighs because you know how much the kilogram weighs. It's the same thing with neutron cross sections. You can say, take something else. I'm not going to name any nuclei, measure it against 6 lithium N-T. So then you have a measure of your neutrons coming in, and then you can measure the cross section of whatever else you're measuring against the 6 lithium N-T. However, unlike the kilogram, neutron cross-section standards are working standards. So they change, they are updated, they are assessed, they are updated, and they are also improved. There are multiple neutron cross-section standards. These are just one, and it actually goes up to 1 MeV. And the reason it goes up to 1 MeV is, you can see here, experiments do not agree very well. So we would like to be able to help to see if we can help extend the standard and see if we can provide more information for what is already there. The problems, and this is where really what was behind this porting over to GPUs really helped, is that as you increase in energy of a neutron hitting 6 lithium, you have many open channels. And these are channels that you need to compute the RGM matrix elements between. So computationally, this is significantly more difficult than, say, doing alpha-alpha scattering. However, once we compute the 6 lithium N-T reaction, I should say this is not what it looks like coming out of the box, but the NCSMC is formulated in a way that parameters can be modified slightly. So the positions of resonances and thresholds can be modified. So we obtained very good agreement for the cross section. But this is not a prediction, right? We just made the line coming to fit the data. What is a prediction, on the other hand, is the angular distributions for the triton. And we observe, again, very good agreement with experimental data. And in fact, in some energies, we're actually doing better than NDEF, which is pretty surprising, actually. And these are predictions in the sense that we have not fitted to the angular data at all. So what was actually surprising in this case is that we found a 1/2 plus resonance, but about 1.5 MeV. It was pretty broad, but it was really what was defining the cross-section at very low energy. So its position was really important for us to be able to describe the total cross-section. And as a result, these are all predicted angular distributions. So with that, I think I am on time. I'm right on time. Cool. So we have made first steps in dealing with alpha clustering. There's still a lot to be done, actually, namely the NCSMC part. The reactions with P-shell nuclei that I mentioned are not only interesting in terms of clustering, which they are on their own accord, but they also give us a foothold to be able to study reactions like 6 lithium transferring in alpha and producing a deuteron to study alpha transfer reactions. And finally, we are still working on making uncertainty quantification possible for nuclear reactions. It is a much more involved process than I would have expected. So, but still, the future is looking bright. So with that, thank you.
Yeah, thank you for the very interesting talk. Are there any questions? So we already had some, but there's obviously time for more. And I see Heiko up, so please go ahead.
Okay, I guess at least you can hear me. Hi, Kostas, very nice talk.
Oh,
so can I even switch on there we go, up in space. So I just had like was wondering whether you could say a few words on what the distinction between low and high fidelity means. So is that like small and max? Is it like just a few configurations for the RGM, or
no, it's E3 max in that case. So lower was E3 max 14, higher was E3 max 16 in that case. The problem, as you know probably better than me, is memory, right? So you need to somehow fit that whole thing in RAM the way we have it now. So the fact that we get similar computational cost for E3 max 14 and E3 max 16, where the file is 5 times larger, is, to me, it's pretty encouraging. It means we can actually go further, because it turns out when you try to do reactions, even E3 max 16 is not sufficient. I mean, it is sufficient, but it's not complete. So if we want to go to higher Nmax, we need higher E3 max. Because if you try to do, let's say, an Nmax 12 calculation of scattering, an E3 max 16 file is nowhere near enough to compute everything correctly. So that's basically
it. I think it definitely answer that, and I think it's actually quite encouraging that you can have like a discrete parameter of your calculation that you can still kind of fold into the whole emulator construction. Right, which is, I guess, not a priori a given that something that it would work for like a discrete, again, control parameter in there. So I think that's seems like a good idea, good thing to try out for other approaches as well. Okay,
so
thanks. Yeah.
Oh, you're. But what I wanted to say was we actually also have a continuous. So if you do importance truncation, you can also base it on a continuous parameter as well. So you can do scattering with importance truncated nuclei. There is no particular difference. But these are things that we're investigating, basically. And yeah.
Good, thanks.
Okay, we have a question from Philomena in the chat. She asks how your Helium-6 plus Helium-6 results compare with data.
I would say horribly. If I can manage to move back. So
I love your honesty.
So the point here was this was a qualitative calculation. I don't know if I mentioned it when I was talking about. So first of all, for this reaction, I don't think there's any data that are, at least I didn't find any data that didn't look like a huge bump of noise, where, you know, take 20 counts and call it a resonance. The other thing is that, as I said, this was qualitative. So this actually used only the NN part of the interaction. So there are no 3 nucleon forces. And we didn't make any effort to actually investigate different interactions and whatnot and see how stable things are. So one striking example is that the ground state is very bound. So it's about, I think, 7 MeV, where the experiment is, I think, 3 MeV, which is to be expected, right? You have a nucleon-nucleon interaction that is softened via SRG. You don't have the corresponding 3 nucleon parts that would push it out again, so everything is overbound. So in general, positions are fairly bad. Also, here we do, however, have the correct number of states, let's say. Sorry. The other thing that I guess may be interesting is that the 10 beryllium plus 2 neutron threshold is also somewhere here. So any calculation we make will be suffering from not having that 2 neutron width. So overall, I would say it's a little bit difficult.
Okay, so actually, this reaction that you have up there, the helium-6, helium-6 alpha helium-8, has been measured at triumph energies, perhaps Ganil energies as well. So it's a relatively low energies, but not, of course, not that close to zero. But in your plot, they would appear somewhere. And I think that there have been the detection of multiple states, excited states in the helium, in the beryllium-12 system. So there's certainly data to compare to, but I appreciate that, you know, you're still exploring the NN sector here. And so the comparison to the data may not yet be meaningful.
So the other, in very many quotes, problem is, for example, these resonances are definitely not at the correct energy, right? So, sorry, this is a cluster resonance. We know which one it is in the spectrum, and it was supposed to be at, I don't know, like 17 MeV of excitation, not from threshold. So now it's at 27. So we know the resonances are way off. And this is a problem with interaction, I mean, and convergence as well. But it is what it is, I guess.
Thanks. Thanks very much.
Okay, Daniel, please go ahead.
Thanks, Kostas. Yeah, that was a really nice talk, and the work is really impressive. I want to try and follow up a little bit on Philomena's question. And I'm going to frame this in terms of a reaction which I know something about, which is beryllium-7 p gamma. So you had that on your last slide. So
I forgot to take it out. Sorry, I had them.
Now it's on your slide, so I get to ask about it. That's the rule, right? Once it's on your slide, I get to ask. So I mean, but the question is really a more general question. So I'm not just, you know, using this as an excuse to ask about the reaction, right? So the question is, so in that reaction, you have a boronate ground state that's, you know, bound by like 100 keV or so, right?
136.
And so, and in general, in many of these systems, as you just alluded to, you have resonances whose position is kind of crucial. Like it's crucial to get the resonance position right in order to reproduce experimental data. So the negative version of this question is, what sort of accuracy in terms of numbers of keV is really realistic up to something, you know, less than n to the 10th LO or something in chiral EFT? And, you know, if that's not going to deliver, you know, resonance positions, the, you know, 20 keV accuracy, then are there alternative strategies that would allow you to use ab initio information at a reasonable accuracy level, and build that into approaches that could then describe, you know, this physics using some combination of ab initio and experimental data?
Oh, sorry. Thank you for the question. In general, I think I touched briefly on the lithium when I showed this, right? So obviously the resonance is not exactly where it is when it comes out of the box. The good thing about the NCSMC is that you can treat those as fitting parameters. You can actually fit the position of resonances by shifting the Noether shell model eigenvalue a bit. You lose in consistency because it's not exactly the same thing that you're inputting, but then you can also change thresholds, which is in a sense also similarly important. So,
but then the question is how you do UQ on that, right?
On what?
So now you have like, so, I mean, you articulated a strategy to do UQ on the ab initio part of the calculation, but then if you start moving NCSMC eigenvalues around, then how do you do UQ on the combination of my, you know, ab initio plus some external input, you know, approach to this problem?
As far as, I guess there are two sources of uncertainty, right? One is the chiral EFT truncation uncertainty, and one is the parameter, the LEC uncertainty, let's call it, that would be propagated. As far as the chiral EFT uncertainty, the way I am planning to treat it, at least, is that it shouldn't matter. This is the method prediction after a prescription, right? So at the end of the day, the full prediction that you have is the NCSMC plus the phenomenological adjustment.
So you're saying that the results with the phenomenological adjustment would still have the same chiral EFT uncertainties as before the phenomenological adjustment?
That's my hope. I cannot prove it in pen and paper.
No, but I mean, but it may actually be much better than that, right? To the extent that things are correlated, right?
Right, but the hope is that I can use the same prescription that I would use in just the simple NCSMC to compute the uncertainty, the chiral EFT uncertainty, you know, calculating at each order and then taking differences.
Okay, so you say you do the adjustment at each order and then you look at the convergence pattern, and if that converges, if the shifts are small, then you, okay.
Because it essentially will tell you, right, that the physics that you've left out do not contribute to this thing, or to this reaction cross-section. All you needed to do was find a resonance at that point with that width, your life's good.
But I guess a sort of a, I'm not quite sure if this is like a metaphysical question or something, is whether there's I mean, you're essentially exploiting intuition about clustering to some extent in order to pull this off, right?
Why clustering? I don't know.
Well, I mean, so this one is here you're working in a system where you have sort of helium-4 and tritium clusters, right? And so
and lithium-6 and neutrons and 5 helium plus deuteron and 6 lithium.
Yeah, I mean, I'm not saying that it's all that's going on, right? But I'm saying that insofar as many of these things that are correlated are going to be correlated because they're correlated through the cluster physics, right? And so it's not so insofar as they're correlated through the cluster physics, you may be able to predict beforehand which observables are correlated and therefore which NCSMC matrix elements are particularly valuable to do this phenomenological adjustment with, instead of having to do it on the back end after the results are generated.
Okay, so we don't adjust all matrix elements. We just adjust.
No, I totally understand, right? So,
no,
but I mean, yeah, go ahead, sorry.
Okay, sorry. Maybe it sounded a little bit different when I said it than when I thought it. I was going to say that the only thing we adjust are the Noether shell model energies of the compound system. So when we add these extra terms that describe the A body NCSM state, all we adjust are the energies of those.
Right.
So there is not much freedom, right? You get as many states as you have resonances, basically. So at this level, you won't have many more states that you can adjust.
But now, what if I want to predict like BE1s or something, right? Am I going to also need to?
It would be a prediction at this point.
But so, up to what accuracy, right? So that, I mean, so but and this is what I'm saying, right? To the extent that the BE1s are related to the energies through clustering, you actually can have some intuition for the accuracy at which the correlation that you want to exploit between the state energy and the BE1 will get you where you want to go, and some intuition for where additional adjustment might be necessary.
Okay, I'm not sure. I haven't thought.
We can. It sounds like I don't want to hijack.
No.
So we can iterate on this too, right?
So the other, I think I mentioned it briefly in the beginning. Eventually, what we would like to have would be one thing that combines the theory and the experiment and produces a value.
Yeah, right.
Not just the theory, and that is the uncertainty of the theory.
Yeah.
And
right. I think information assimilation is an excellent goal here, right?
So the good thing here is that the underlying thing is the R matrix.
Yes.
So at the end of the day, it makes little sense to actually, as I had before, try and have U2 for the entire cross-section as a continuous function. What I need is an uncertainty on the R matrix parameters, and that will propagate into whatever I want, and it's much simpler.
I completely agree. Yeah.
So I'm not gonna say we didn't make any mistakes in planning, but
No, I think that's I think some sort of intermediate scale approach like R Matrix that allows you to integrate experimental information into some intermediate radius and ab initio information out to that radius and then sort of assimilate everything is a really interesting way to think about this problem. Yeah.
happily, that's what's going to be paying for 30% of my salary next year. So
Excellent. Okay.
Okay, if there are no more questions, then I would like to thank you all for coming. And I hope to thank you again, Kostas, for the excellent talk. And I hope I see you all in 2 weeks.